Hi everyone, this is going to be a video walkthrough of problem 1, which is identifying sorts on the basic sorting exam prep worksheet number 12. Okay, let's dive in. So the prompt states, below you will find intermediate steps in performing various sorting algorithms on the same input list. These steps do not necessarily represent consecutive steps in the algorithm. That is, many steps are missing, but they are in the correct sequence. For each of them, select the algorithm it illustrates from among the following choices. So we have insertion sort, selection sort, merge sort, quicksort, and heap sort. Okay, and it says when we split an odd length array in half in merge sort, assume the larger half is on the right. So just to recap, we are given this input list, okay? And then for each one of these parts, we're given a series of steps in a sorting algorithm. And our task is to figure out what sorting algorithm it is for each part, okay? So let's just get started with part A. And before watching this video, I recommend two things. First, make sure you all have watched the necessary lectures on these basic sorting algorithms. Because if you don't know the algorithms, it's going to be pretty hard to identify which one is which. And the second thing I recommend is before you watch this solution walkthrough, make sure you've given this problem an honest try. So with all of that in mind, let's look at part A. So looking at part A, what we will notice is that we can kind of think about the series of steps that we're given as sorted runs. And this may be a big step, so let's kind of see what I mean by that. And what I'm going to do is I'm going to start from the last one. What I can do here is I can break up the final array or this final sequence of integers into two runs. And when I say a run, I mean a sorted subsequence of numbers. Also, this color is like not too aesthetic, so I'm going to choose a nicer color. My apologies. Okay, hopefully that's a bit nicer to look at. So we can kind of see here there's two runs, right? This is one run, and then, oops. This is one run, and then this is another run, okay? So if we look back at previous steps, we see that we can similarly break them up into runs, right? So we can kind of see here that it's merge sort, but I want to provide a bit more rigorous explanation here. So we know that intuitively looking at this list, it's a bunch of sorted runs, but let's see exactly why it's indeed merge sort, okay? So what I'm going to do is on this right-hand side, I have all of the steps of merge sort. So this may be a bit intimidating to look at, so let's kind of walk through this together. So what we're going to notice is that this is the starting. Oh, can I change? Okay, it's a bit big, my apologies, but this is the starting state of our array, okay? Looking at the starting state, we'll see that the first thing we're going to do in merge sort, right? We can kind of break it up into two stages. I'm going to walk through this first stage. This first stage is like our dividing stage, right? Where we have one large array and we kind of keep breaking it up into smaller and smaller pieces in half, right? We break it up into a half here, then we break it up into more halves and so on, right? Until we have divided the given array into a bunch of 1 or 0 element arrays, right? What we can see here is that we successfully divided up the given array into all of these 1 element arrays. Now what we're going to do in merge sort is we're going to take adjacent runs and we're going to merge them together. So we're going to take this run right here and we're going to merge it together. And in doing so, notice the order doesn't change, right? Then what we're going to do here is we're going to take this run, just kind of move it down. We're going to take these two runs and sort them like so. Then we'll take 594, just move it down. Then we will take these two runs and sort them like so. 492 just goes down. And then we will sort these two runs, right? And what we'll see is that the only thing that we actually like change in the ordering after this first merging pass, right, we can kind of think about these as our merging passes, is that this is the only real change that happened. So a natural question you may all be asking is, why did we decide to merge these two together and these two together, but why was 7683 just kind of like didn't do anything this time around? The reason for that is if we look at the corresponding divide pass, if I look at this divide pass right here, notice that these two elements and these two elements were part of the same group. So what we do is that we say these two elements were part of the same group, so let's merge them together down here in the same manner as these pairs. Okay, so with this in mind, what we're going to notice is that this run right here is actually the first answer. Okay, you can kind of look at that and convince that for yourself. So we have seen the first one, so let's keep going. Okay, the next merging pass, we continue the same behavior, right? We take adjacent runs and we sort them together. So what we see here is that we're looking at this divide pass, which corresponds to this right here. So I say 1429, 1429, and 31, or 1429 and 3291, you stay in the same ordering because you already sorted. But now when we're looking at this run, we see that it's sorted like so, after we just kind of move 192 here. Then if we look at these two runs, we sort them, just maintaining the same ordering. And then here, we see that we sort them by moving 129 to the front, right? So what we can see here is that this is our second answer choice, or the second sequence in part A. Okay, and let's just do the final one. So now what we're doing here is, at this point in the algorithm, we have 4 sorted runs. So what we're going to do is take those 4 sorted runs and make them into 2 sorted runs. How we're going to do that is we'll take these 2 adjacent runs and we'll merge them together. In the same fashion, we'll merge these 2 runs together. And what we'll notice is that after merging these 2 runs, we get this run, and after merging these 2 runs, we get this run. Okay? And what we can quickly convince ourselves is that this indeed is, let's use, I don't know, this color. This is the last choice here. Okay? So that is a very rigorous walkthrough of part A. So let's move on to the later parts, which may not be as rigorous, but we will still completely understand the solution. So moving on to the next part, what we're going to notice here is that, let's look at this started input list before. I'm just going to kind of move it as the first step here. Okay. Okay, there we go. So the idea here is this is what we start off with, right? This input list. And what we'll notice is that the only change from this input list to the first step that is shown is that this number 1337 hops here, right? And what's also going to change is that 192 hops here. And what's also going to change is that 594 hops here. And then we will also see that 129 hops here, 1000 hops here, right? Then what we'll notice is that 1429 hops here. And then what we'll notice is that 3291, 7683, 424, 9001, and 4392 hop like so. Okay, so these are the changes from the input list to the first step that's shown. And what we can pretty easily see, not pretty easily, but what we can notice after this coloring that I got lucky to do was that all we're really doing here is taking this first element 1429 and putting it in the middle, right? And what we can notice is that all of the yellow numbers have been partitioned to the left of 1429. In the same light, all of the blue numbers have been partitioned to the right of 1429. And what this shows us is one step of quicksort, right? Let's recall in quicksort, all we do is that we take this first element and we say you are the pivot. As the pivot, all of the elements that are less than you go to the left. All the elements that are bigger than you go to the right. Okay? So even after only looking at this first step, we can pretty rigorously conclude it's quicksort, but let's look at later steps as well. Okay? So what we can say is that 1429 isn't going to change, so it's always going to be here, right? So let's look at the next step. We'll take 192, actually we'll take 1337, and then we will say let's partition this first subarray about 1337. How that's going to look is 1337 will pop here, and then all of these other elements happen to be less than 1337. So they stay like so, okay? And then what we will do is we will partition all of the later half elements about 3291. So we put 3291 here, and then what we'll notice is that all of these elements happen to be bigger than 3291, so nothing really happens. Oh no, can I find the same color blue? There we go. Okay, so now let's do the last step that's shown here. What's going to happen here is that we will take 192, put it here, right? And then we're going to partition these other elements about 192. So then what we'll see is that 129 is the only element that's less. And then all of these other elements, like 594, 1000, and 1337. Actually, 1337 has already been finalized from the previous round because it was chosen as a pivot. So this is all that happens in the last step of the quicksort that's shown to us here, okay? In a similar light, what we can see is that when 7683 is the pivot, we put it here, and then all of the other elements happen to be less. Okay, so hopefully that walkthrough of quicksort made sense, so let's move on to part C. Okay, as usual, let's start off by looking at the input list, kind of like side by side with the starting array. Okay, so in this pass, what we'll notice is that if we look at all of these elements, the only difference is that 1337 kind of hops to the front, right? That's the only difference we can really see here. So in order for 1337 to move to the front, and in order for all of these other elements that are kind of later in the array to stay the same, it speaks to insertion sort, right? Recall in insertion sort, what we're doing is we're building a sorted array from this left-hand side forward, right? We're kind of building a sorted array like so. But isn't that what we're also doing in selection sort, you may ask, right? In selection sort, we're also building a sorted array from the front, right? In both of these sorts, what we do is we kind of like build a sorted array coming from this left-hand side until it encompasses the entire array. So why isn't this selection sort, and why are we leaning towards insertion sort here, right? So what we'll notice is that in selection sort, we take the smallest element and we move that smallest element to the front. But 1337 isn't the smallest element in the array. So what we can see here is that this is insertion sort because in insertion sort, we first move all of these elements to the left. They don't do any movement. Then we take 1337 and then we move it all the way to that first spot, right? All we do in insertion sort, just to recap, is we look at each element and then we keep swapping it to the left until it's in its happy place, That is, we keep swapping it to the left until it is bigger than the element to the left of it, and then we stop. Okay, so what we'll notice here is that this was kind of like that first swap that happened. Okay, now let's kind of look at the next step just to convince ourselves this is insertion. So it will be really rigorous here. What we're going to see is that all of these kind of stay the same here, but the difference is that we take the purple people, put them one to the right, and then we take 192 and put 192 here. Okay, and then if we look at this last pass, what we'll see here is that all of these people are the same. And now what we've done is we've taken 594 and slid 594 to the second spot. So we can pretty rigorously conclude that this indeed is insertion sort, because all we're doing is we're kind of starting from the left-hand side, moving to the right, and taking each element and kind of sliding it in its correct position. So what we can do is claim that this is insertion sort. And I've realized I've kind of like neglected writing these answers. So the first is merge sort, the second is quicksort, and the third is insertion sort. Okay, but hopefully it was made clear by me just explaining it to you all. So let's move on to this last one. Looking at this last one, we have this input list given, right? Okay. Okay, so we have this given input list, and what we will notice, the difference between the starting array, right? This is the starting array, and the second array, the second step that we have here, is a lot of stuff has changed, right? It's kind of confusing, like what in the world is happening? So let's try to figure out, like, are there any striking things that we can notice here? So one pretty weird thing that's happening, at least I think weird for me, is that how did 192 go from here to here, right? It's kind of strange in a sorting algorithm to take a small element and put that small element at the end, right? Let's kind of like walk through the sorting algorithms that we're given and ask ourselves, like, which sorting algorithm could possibly have such a behavior, right? So insertion sort wouldn't do that, because insertion sort just moves the smaller people to the left. Selection sort, in the same regard, just moves smaller people to the left. Merge sort also wouldn't move a smaller element to the right-hand side. And we can also see that quicksort, since we've already seen it, we can eliminate it, but it also wouldn't do such a drastic change. Okay, so just by process of elimination, we can kind of like conclude it's heap sort, which intuitively should make sense because heap sort works a little counterintuitively. That is, in heap sort, what we do is we first take the given array and then we make it into a max heap. Okay, so in making the given array into a max heap, what we've kind of done is that we've taken the smaller elements and put them at the end of the array. We've taken the bigger elements and put them in the beginning, right? So we can kind of see it works a little differently than other sorting algorithms we've seen so far. And just to be really rigorous here, let's walk through the steps of heap sort, okay? So just to, I don't know, provide a very, very just explanation here, what we'll notice is that this is the starting state of our array, okay? The first step in heap sort, let's recall, is we take this given input list and we kind of visualize it as a heap, okay? Now what we're going to do is we're going to take this heap, or take the current state of the array visualized as a heap, and make it into a max heap, right? So what we're doing here is that we're trying to take this and move it into a max heap. So let's kind of like walk through those steps of taking this and making it into a max heap. So we have this state right here. And what we're going to do is that we're going to keep bubbling everybody down, starting from this element right here. Okay, so what we'll notice is that for all of these elements, there's no bubbling down that needs to be done, even 594. So what we'll see is that when we go to 192, we swap 192 with 1000. Right? Because after bubbling down 192, we're creating a max heap, so 1000 fills the void. Okay? So I'm going to create a duplicate here just so we can kind of see like the change over time. So the first change that we did is 1000 and 192 swap. Okay, and if this is redundant, feel free to like stop the video, but I just want to make sure that people understand like why exactly this is heap sort. So we're just walking through the steps of heap sort on this given array. Okay, so what we've done so far is we've bubbled down all of these elements. Okay. Now the next thing we'll do is bubble down 1 through 3, 7. So what's going to happen here is after bubbling down 1, 2, 3, 7, we will have 9, 0, 0, 1, and 1, 2, 3, 7 kind of swap like so, right? Okay, so what we will see here is that if we take this state of the heap, we put it as an array, right? We will see that that's the exact same as this array is the exact same as the first step in the algorithm, right? And you can kind of look at this heap, kind of translate it over and convince that for yourself. Okay, so we're still making it into a max heap. So we have a couple more steps, but I'm going to cut those steps just for the sake of time and kind of move in here that state. Okay, so what we've done is that I kind of skipped 2 steps in that we bubbled down 7683, 3291, and 1429. Okay, those are the steps I've kind of skipped here. But after bubbling down everybody, we get this max heap right here. Okay, so we kind of label it as a max heap just for our understanding. So we have this max heap. Okay, so now that we have a max heap, what we want to do is take this max heap and make it into a sorted array. How we're going to achieve that is we're going to keep removing the maximum value, putting that maximum value at the end of the array, and repeating this process. Okay, so what we'll notice here is that the first step in this actual heap sort algorithm, right? First we make a max heap, then we kind of like keep performing this remove max, put max at end. The first step of that is we take out 9001, we temporarily promote 192 to the top, then we're going to bubble down 192 until our heap properties are fulfilled. Okay, so now what we're going to see here is that if we take this state of the heap after one remove max, we will see it kind of looks like 7, 6, 8, 3, 4, 3, 9, 2, 4, 2, 4, 2, 3, 2, 9, 1. And then we can see that that is going to be this state right here. Okay, so we've seen 2 of the states so far, but we're still missing one of these states, right? And there's one small thing here is that this heap has one less element than the previous heap because we removed 9001. So you may be looking at this array and saying that like 9001 isn't the last element of this heap. Well, it isn't the last element of the heap because at this point in the algorithm, after we perform one remove min operation, our heap, it only contains these elements right here, okay? Because we know that 9001 has to be the biggest person in the entire array, so we put 9001 at the end. Okay, so if we want to be like really rigorous here, we can say that this is our heap, and then this is the element we removed from the heap. So the state of our entire array should also include 9001, right? Because it belongs there. Okay, so now what we're going to notice is that let's do one more step of this heap sort. And the next step, what's going to happen is we're going to remove 7683. We're going to put 129 there. And now what we're going to notice is that that is going to be the final state that's shown here. Okay, so if we look at this state, what we'll notice is that that's the exact same as this current state of the heap with 7683 and 9001 tacked on at the end, right? So more rigorously, if we kind of look at this heap, we can see it goes 1, 2, 9, 4, 3, 9, 2, 4, 2, 4, 2, so on. And this is the state of the heap. And then the elements that we removed from the heap so far are 7683 and 9001. Okay, so this is the state of the whole array. And that's the last step that's shown here. Okay, so hopefully this walkthrough helped solidify your understanding. And yeah, stay tuned for the next one.